In this video, for the sections 3.3 and 3.4 activity, we're going to talk about annuities and sinking funds. Annuities are sequences of equal periodic payments. So the difference between the annuity formulas and the compound interest formula is that in the compound interest formula, we put an amount of money into the account once. In the annuity formulas, we're putting money in every month or every year. So instead of the principal in the formula, we have this PMT, which is that periodic payment amount. So in this section, we are going to be doing problems that are going to involve investments and savings accounts, other things where you're making money. In the next video, we're going to tackle loan problems where you're paying money. So we have this future value formula. It's FV equals PMT times 1 plus I to the n power minus 1 over I. So FV is the future value, pretty much the same thing as the A in the compound interest formula. PMT is that periodic payment amount, so the amount that you're putting into the annuity at a regular time. I, interest rate per period. This is the same as we saw in the compound interest formula. I is equal to R over M, where R is the interest rate. And you need to convert that to a decimal. And M is the compounding period. So the number of times compounded per year. And N is the number of payments. That's equal to M times T. So if it's compounded monthly, for example, your M is going to be 12, and then T is number of years. So we have this formula that gives the total value in the annuity. We also have a rearranged version that we can use to calculate the payments needed to reach a specified future value. So if we know the amount that we want to save up to, we can figure out how much we need to put away each month or each year in order to reach that amount eventually. So looking at problem 1, it says a company estimates that it will have to replace a piece of equipment at a cost of $800,000 in 5 years. To have that money available in 5 years, a sinking fund is established by making equal monthly payments into an account paying 6.6% compounded monthly. How much should each payment be? So a sinking fund basically is a savings account that you set up to reach a certain goal. In this case, our goal is to save $800,000 in 5 years. So we need to figure out how much we need to put away in order to make that happen. So we're going to use the bottom formula here that's going to give us the payment needed for a specified future value. So we're going to plug in $800,000 for that future value. And then we have this fraction here. My I is going to be 6.6% compounded monthly. So that's going to be 0.066 over 12. And then I have the same I down here in the denominator. And then here I'm going to have for my exponent 12 times 5 because it's compounded monthly. And we are saving over 5 years. So 5 for T and 12 for M, and then I have a minus 1. So now I'm going to plug this in on my calculator. Really important that you plug it in correctly. The decimals calculator makes it really easy to do this correctly. If you're trying to do it on another type of calculator, like a phone calculator, you might have a little bit more trouble. So 800,000, I like to use the A over B button for these problems because it makes it a little bit easier to get the fractions. And 0.066 over 12. And then in my denominator here, I need parentheses. Whoops. 1 plus another A over B my power is going to be 12 times 5. I know that that's 60, but I can also just type 12 times 5 in my exponent. If I do that, I need parentheses. And then don't forget that minus 1. So here's what we have, $11,290.42. So that's the amount that I need to be putting away each month in order to reach my $800,000 goal, which sounds like kind of a lot, but $800,000 is a lot of money, and 5 years is not really that long. So this is how much needs to go into the sinking fund every month. So moving on to question 2, Jane deposits $2,000 annually into a Roth IRA that earns 6.85% compounded annually. The interest earned by a Roth IRA is tax-free. That's not really relevant to the problem. I think that comes from the book. Yeah. So for part A, we have Jane makes deposits into this account for 10 years. Find the amount in the account after 10 years. So now we're going to use this first formula in the box because we want to find the future value for a given payment. So we're putting $2,000 in each month. We want to know how much we will have in the account at the end of that time. So I'm going to have FV, future value, $2,000, and then my fraction here. So we're going to plug in. Now for this one, we have our 6.85 interest rate, and that's compounded annually. So for I, it's going to be 0.0685 divided by 1. Since compounded annually means it only happens once a year, so that's just 0.0685. So that makes it a little bit easier. When it's compounded annually, there aren't quite so many buttons to push. And then for my exponent, it's going to be 10 years. So this is going to be 10 times 1, or just 10. And then don't forget, we have a minus 1 after that. And then we have I in the denominator. So we have minus 1. And then divided by 0.0685. Type that into my calculator. Now, one thing that you might want to do, this isn't required, but you might find it helpful to take screenshots of the calculator and put them in your notes instead of writing things out. The calculator looks a little bit neater, and that also might help you in terms of being able to do the problems again later. So again, not required, but a recommendation. So 1 plus 0.0685 to the 10th, and then we have minus 1 divided by 0.0685, and that gives us an answer of $27,437.89. So I'll write that. $27,437.89. For part B, after these 10 years, Jane switches jobs and she's no longer making deposits into this account, but it continues to accrue interest. Jane retires 25 years after the last deposit was made. How much is in the account when she retires? And the hint is to use the compound interest formula. So I'm no longer putting money into the account. So we're going to switch this to now this is basically a lump sum that we're starting with, and we're earning interest on that. So that's why it switches. So now this is going to become my principal P. So $27,437.89. And then assuming my same interest rate of 6.85% and compounding annually, and then my power here is going to be 25. So this is actually a really common situation that happens when people change jobs. They might roll their retirement account over into a new IRA, but they're no longer putting money into that account because now they have a new account for their new job. And so their old account, you're not adding money to it, but it's continuing to earn interest. So what I like to do in this case is use the answer button to pull in my answer from the previous problem. And then I have 1 plus 0.0685 raised to the 25th power. So I'm going to have $143,785.10. So let me write that here. So it's kind of interesting, and this shows that the really important thing about investing and retirement is the time factor. So for the first 10 years, when she was putting the money in, after those 10 years, she ended with a total of $27,000. 25 years later, she didn't put any money in. This is all interest. So the interest is almost $120,000 on that initial investment. So the time is really what, because the interest rate is not changing, and the interest rate here is not particularly high, but it's really that 25 years that allows it to grow so much. And this should say what was the total amount Jane deposited. She deposited $2,000 a year for 10 years, so she deposited $20,000. So in that 10-year time, her investment grew $7,000, but then after that, that 25 years after that, it really grew a lot more. So the advice that you see is always to start early with retirement, start saving in your 20s, and that's time that you need to really build up your retirement accounts so that you have a lot of money when it's time to retire.